Thanks for inviting me here to give this presentation about some of the work that we've been doing at Microsoft Research. So yeah, my name is Kim Laine. I'm a researcher in the Cryptography and Privacy Research Group in Redmond near Seattle. Our group, I guess I have this silly slide here because I often give these kinds of talks to like academic audiences and try to recruit people. So we often our group does all kinds of things. Actually, we do things like theoretical crypto protocols, machine learning, privacy research, some blockchain, but we also do a lot of implementations. We build systems from modern cryptography. We look at IoT device privacy, hardware acceleration, GPUs, FPGAs, how to accelerate some modern crypto with that. And then finally, we also look at usability. We build libraries, we build APIs, and we are even doing some user studies. We do a lot of user education and trying to make the experience for developers more pleasant for modern cryptography. All right, well, agenda. So let's start with some corporate fluff. Of course, typically when we want to motivate some of homomorphic encryption and some of this modern cryptography work, other secure computation techniques too, we bring up these 3 stages of data privacy, and this is also why kind of Microsoft cares about this, which is that when data is in transit, of course, it must be protected. This is very easy. Just use TLS. When you're storing data long term, you can use AES, and it's very well known. But then once data is in use, somehow it should also be protected. Actually, NIST recently released this draft of this thing called Privacy Framework. It's a very, very, very impressive document that kind of tries to help companies set up and organize and classify their privacy policies, and also gives concrete and measurable steps to implement them. In this draft, they mentioned the first 2, but they didn't mention the 3rd one. So actually, a couple of companies sent them feedback that they should add that data in use must be protected. Well, surprise, surprise, one technique for protecting data in use is homomorphic encryption. But there's also a couple other techniques, such as secure multi-party computation or maybe some secure hardware. There's all kinds of variants of that. How many people are kind of a little bit familiar with homomorphic encryption? Well, that's expected. Right, so of course, again, why does Microsoft care? It's because our biggest business is cloud, and of course, Microsoft Cloud is very, very much trusted, but some other clouds might not be as trusted. But more generally, when you use your cell phone and use all kinds of apps and services, you don't really know what they use for the backend, and you don't really know if you can trust that, and you don't know if you can trust the service, whoever created the service. So who gets access to your data? And in a classical setting, unfortunately, what happens is that you have your data locally. You choose a key, you encrypt it, you can store it long term. But as soon as the service provider needs to do anything with the data, they need to get access to your key, and they decrypt the data, compute, they can re-encrypt the result, I guess, and toss the key. And this is all basically access policy restricted, not cryptography restricted, not cryptography kind of controlled. And then you send the result back, and you get the result. Well, obviously there's a vulnerability. Now, when you think of all these new cloud services, all kinds of new apps and tools that are coming up, it's very common these days to use to share health data, to share financial data, calendar data, location data with all kinds of service providers. Like when I travel to different places, I'm not. I'm sharing my location with Google. I'm sharing what I'm looking for breweries, and I'm sharing that where I'm going, and I'm sharing all of that basically with these service providers. In some cases, of course, that might be okay. In some cases, you might say that, well, doesn't really matter. But there are also situations when you might not want to share that. And the unfortunate fact is that there aren't really any options. So you either don't get the service or you have to just, hit accept. And kind of, it would be sweet if there were some options. So what homomorphic encryption is a new kind of encryption. So it's not like AES, not like RSA. And I don't know if I need to explain that to this audience necessarily, but often we get, when I explain this to some customers, for example, they kind of misunderstand this point. They think that it's like AES and then we somehow decrypt it very quickly or something like that. It's not like that. It's very different from those. And what it allows you to do, it allows you to compute directly on encrypted data. And that's the idea of homomorphic encryption. So I can take my data here, I can encrypt it, and I can send it to the cloud, and now, or whatever service provider, and now the service provider can actually perform a computation directly on the encrypted data. So the key is not shared at all. So the idea is that it's kind of end-to-end secure, end-to-end encrypted. So they get the result and send it back to me, and I can decrypt the result and obtain the result. So this is the kind of promise of homomorphic encryption. The reality is kind of close to the promise. But there's a lot of practical challenges in this one, which I'm getting to. So actually, homomorphic encryption was kind of discussed already in the 1978, I believe. But there was no real construction known at that time. And only in 2009, this Craig Gentry, I guess he was studying doing some patent law. Maybe he was like a patent lawyer or something like that. And then he was like, well, they haven't even figured this out, so let me just create this fully homomorphic encryption scheme. So he had this really revolutionary paper that created the first such encryption scheme. I mean, normally when you take AES encrypted data, there's no way you can compute on that because it's totally garbled. I mean, this is also totally garbled, but it's garbled with some mathematical structure. Today, well, actually, already from the beginning, Gentry's construction of homomorphic encryption, the hardness of that, the security of that, was based on some high-dimensional lattice problem. And these kinds of problems are very nice because, in fact, it's not known how to break them with quantum computers, so they're basically, we call them post-quantum secure. And actually, NIST has this post-quantum conference series where they try to decide which kinds of crypto systems to select for standards. And many of them are based on these kinds of assumptions. Today, actually, many of them use either the learning with errors assumption or the ring learning with errors assumption. And these two, well, learning with errors is, it's kind of, it's an interesting problem. It's like a linear algebra problem, almost. So you can think of a system of linear equations, modulo some prime number p. And it's a big system. Now, normally this kind of system would be easy to solve. You could just do Gaussian elimination or whatever. But this is a little bit different. This is a linear system plus some epsilon, some kind of perturbation. And now what happens when you start doing this Gaussian elimination, this perturbation is actually very small. But when you start doing Gaussian elimination, you're going to have to divide by stuff. And or multiply by stuff. And what's going to happen is that arrow is going to blow up. And it's going to completely mess up your Gaussian elimination. This is why there is in fact no good way of solving this sort of approximate linear algebra problem, modulo a prime number p, when the dimension is high enough. And somehow miraculously, what this still allows us to do is it allows us to evaluate the circuits. So these could be either maybe Boolean circuits or arithmetic circuits over encrypted data. So basically, you could like evaluate polynomials on the encrypted data, and the result remains encrypted. Well, here's some two equations that I guess kind of capture everything that I just said. So if you take an encryption of some number A and encryption of some number B, and you sum them, and then you decrypt that, you kind of get A plus B, and same for multiplication. Of course, this is extremely misleading because, in fact, these two here are not just like the operations on the right-hand side. These are some very complex operations because this encryption of A, encryption of B, those ciphertexts, they're not like numbers. They're some very large polynomials. And these operations are not like very simple at all. So it's actually much costlier to operate on the encrypted side than on the unencrypted side. So when you start looking into homomorphic encryption, there's actually many homomorphic encryption schemes, so it's not just one scheme. The field has developed a lot since Greg Gentry published his original paper. And today, the most popular schemes are probably this BFV and CKKS, and these are named after the authors. BGV is also kind of popular. But these have very different properties. So with BFV and BGV, you can compute encrypted modular arithmetic. So if you have some number, modulo prime p, and another number, and then you can encrypt these, and you can kind of get the modular arithmetic to happen while doing the computation kind of only on the encrypted, on the ciphertext. Actually, a little bit more accurately, these both schemes actually, or all three here, they really operate on vectors of numbers instead, not really on individuals. And I'm going to come back to that soon. It's a very important point to understand. This BFE and BGV, because they operate on kind of these modular integers, they're good for exact computations. But of course, if you want to do integer arithmetic, then you need to ensure that your modulus, because this is modular arithmetic, right? So you need to ensure that your modulus is so large that your integers don't wrap around that modulus at any point during your computation. But it can be a little bit difficult because you have some like encrypted values and you don't know what those are. So how do you estimate if it's going to wrap around or not? So you just kind of have to, well, I mean, you can estimate, but it can be a little bit challenging. There's another scheme which is much newer called CKKS, and this one is very nice because it allows you to encrypt and compute on real and complex numbers. Well, actually what it does is you give it like a double, or actually give it a vector of doubles. It also works on these vectors instead. So you give it a vector of doubles. What you have to do is you have to scale it up first to integers, and then you kind of compute on integers. But it's very different from this one. There's a really fundamental difference. Because on the left-hand side with these schemes, there's no way to divide. And that means that when you start computing, you could even take some rational numbers here and scale them to integers, and you could then compute on those. But the problem is that now you just like accumulate all of that precision. And it doesn't matter, like it's like irrelevant to you, but you can't divide, so you can't get rid of the extra precision. And you're going to quickly wrap around your modulus. But with the CKKS scheme, you can actually wrap around, you can actually divide, and you can get rid of the unnecessary precision that you have accumulated. So in that sense, while this CKKS only results in approximate results, you can kind of tweak how accurate it is, and it's very good for things like machine learning applications where you don't really necessarily care about exact results anyway. There's also a third kinds of schemes, for example, this TFHE and FEW, which operate on encrypted bits. they're good for non-arithmetic computations. With these first two, or the top row schemes, it's very difficult to do, for example, encrypted comparison. If an encrypted number A is less than an encrypted number B, I mean, you're supposed to do some kind of magic there, and out should come either an encrypted 0 or an encrypted 1, indicating which one was bigger. But this kind of thing is very difficult to do with the first two. Except maybe with CKGS you can kind of do it approximately, but it's like not great. But with the TFHE, because you have the bit decomposition, everything has to be in bits, then you can easily do it.
So in the last two, is it possible to do non-linear operations, like I can find a maximum of a small number?
It's certainly possible, yes.
With the last two,
with the TFHE and few, yeah. Because everything is just bits. I mean, you have to express everything as a Boolean circuit. But then the problem is that now even a very simple, if you have any simple arithmetic computation, it becomes like hugely complex and very, very slow. So none of these is perfect. You would really want to mix and match, and some work has been done towards that, but it's not easy. Okay, so I'm actually a very practical kind of guy. I implement this stuff a lot, and I talk to developers a lot. I work with developers a lot. I mean, I guess you could call me a developer, kind of. But I also help people build systems from this, and I educate a lot of developers on this. Now, so it turns out it's actually quite difficult to program with this stuff. And actually, it's true for all encrypted computation, not just homomorphic encryption. It's also true for secure multi-party computation, and well, I guess that's the only real alternative. One fundamental reason is that there's no branching on encrypted data. This is obvious, because otherwise you would leak some information about the underlying plaintext data. So that is. You can't do like a binary search. So if you want to search a list, you have to do it linearly. Typically, developers are not really comfortable expressing their computations as circuits. Homomorphic encryption specifically has an interesting kind of, maybe you could call it a cost model, where the multiplicative depth of the computation that you do, that's what matters. So if you want to evaluate some huge sum with like 100 billion summons, and this is possible. But if you want to do something like compute a product of 1,000 numbers, well, that's difficult, or more difficult. And last, in most homomorphic encryption schemes, the plaintext are large vectors, like I just mentioned. So here's an example of, well, two vectors. They're not large, they have 4 elements, but in practice these vectors can be like 16,000 or 8,000 elements, so that they can be very large. And now actually when you encrypt this, indeed it encrypts the entire vector, and when you do computations it does it in this SIMD fashion. So it does it slot-wise. Fantastic, you say, free SIMD, and this is like natively baked into the encryption scheme itself. There's no way to not have this property. If you think about it a little bit more, this means that if you want to take data, you want to encrypt it and store it in a cloud service for later use, you actually have this weird vectorized storage thing going on, and you have also vectorized computation going on. So this is a little bit difficult to deal with, because it's not necessarily free to extract the individual slots from these vectors. That costs something. And when people would ask something like, well, can you somehow integrate this into some SQL server? It's impossible. Like, you would have to do some incredible rewriting and rethinking of the entire system because of this vectorized storage. Like, how would you do it? I mean, if you know how to do it, let me know. But it's like a huge pain. So that's one challenge. Another interesting thing, I wanted to tell you something about this concept of noise. which as soon as you read anything about homomorphic encryption, you're going to run into noise. So noise means it's a concept that is related to the security of the encryption scheme. So almost every homomorphic encryption scheme has this noise, except maybe some really obscure ones that I have never heard of. It's possible that there's something, but the way this works is that when you encrypt a ciphertext, when you encrypt a plaintext and you obtain a freshly encrypted ciphertext, it has some amount of noise, so-called noise in it. And when you do computations, specifically multiplications, the noise increases. And once it reaches like a maximum level, then the ciphertext is corrupted. And you can't decrypt it anymore. Now, there's another core concept called bootstrapping. And this was one of this Craig Gentry's great inventions. The idea is really, really neat. So suppose you start computing from that, on that fresh ciphertext, your noise increases. It gets up to some level. Now you can't compute anymore because it would get corrupted. But now what you can do is you can kind of encrypt it under a new layer of homomorphic encryption. So you take your old the ciphertext that has like maxed out noise, you encrypt it under a new layer of homomorphic encryption, and you kind of run the decryption circuit with the help of an encrypted version of the secret key. So you can kind of like decrypt the ciphertext under a new layer of homomorphic encryption. And what this does is it kind of refreshes the noise. And in principle, you can do unbounded computation. And with some schemes such as this TFHE and this a few these Boolean schemes, you actually can do this. They were specifically designed to have very fast and very efficient bootstrapping, so you can truly evaluate arbitrary Boolean circuits. At least in theory. And in practice, it's not necessarily very efficient. So here's a little ridiculous graphic, which is of what I just explained. So you start with a fresh noise. There's some noise max. You compute more. Now you're filled up. You can't compute anymore on this. But then you do a bootstrap, and it brings it down to a kind of fixed level. And then you can compute more. And then you can bootstrap again. Yeah?
Is the maximum noise predictable then?
It's very much predictable, yes. The maximum noise depends on the encryption parameters. So when you set up your homomorphic encryption scheme, you have to choose these encryption parameters. And choosing these in an optimal way is kind of an art. These parameters easily determine the maximum noise. And the bigger the parameters are, the more, well, we say the bigger the parameters are, the more noise room you have. It's like the higher the dimension of the lattice is, the more noise room you have, basically. And on the other hand, if the lattice dimension is smaller, then you have a more efficient scheme in terms of like computational performance. So the kind of the smaller the bar is, the more efficient computationally it is. So there's this choice that you have to make: how much computation versus performance. Okay, well, this is there's this really silly issue now going on that the developers of this CKKS scheme, people from the same university, they had a paper, or they had a couple of papers about bootstrapping for this approximate scheme, CKKS, but it has a slightly different meaning there, and it's now created this dual meaning for the term bootstrapping. Well, sad face, because bootstrapping has a very steep performance overhead. Actually, most people don't do it at all. There's also other usability challenges with it. It's very difficult to use. But there was this thought that, well, what if we don't bootstrap at all? Let's just choose the parameters to be big enough so that we can do a specific computation that we want to do. Now, this means that you don't just like start from an arbitrary. You don't allow arbitrary computations, but you have to decide what is the kind of computation you want to do. But from a sort of privacy policy point of view, if you think of a company, for example, that wants to collect your data, and they have sound privacy policy, then that privacy policy should also say kind of what kinds of things they do with your data. Of course, today that's not usually how it works. Today, the data is put into some data warehouse, and data scientists at a later point start looking at it and cleaning it up and thinking about, what could we do with this, and then they try to, like, at a later point still extract even more information from it. So of course, it's not exactly like that today, but ideally companies would ahead of time decide what they want to do with the collected data. Okay, in most homomorphic encryption schemes, therefore, what we have is this kind of SIMD, vector negation, addition, multiplication, and because we are dealing with vectors, it would be nice to have some vector operations, and we do have that. It's possible to do an encrypted vector rotation, which means that it's possible to do an encrypted vector, some slots kind of thing, which sums all of the values in the individual slots. It's possible to filter out specific slots. Right, in some other schemes, like CKKS, you can do this complex conjugation because you can encrypt actually complex numbers. And hypercube rotation, well, in some schemes, it's possible to parameterize them in some very intricate ways, so that it's not actually a vector, it's some like multi-dimensional objects, and then you can do these hypercube rotations. But I think a lot of people don't really have that many use cases for hypercube rotations. You can also do bootstrapping in some schemes, in some libraries. So good news is that if you want to use this stuff, it's actually possible today, because there's a lot of active implementations existing, and these are all open source. So many of them are written in C++. Actually, so Microsoft Seal is our library. And many of these are in C++. Ladigo is in Go. Good choice. We also have C# wrappers. I don't know how many people love C#, but at Microsoft, it needs to be in C#. Well, we have, okay, good news. We have .NET standard wrappers, so at least it's like cross-platform, right? So it works. It's pretty good. 4 of these libraries implement either BFE or BGV. Again, these are the modular arithmetic schemes. These are much older. And now we have 5 of the 6 libraries that implement CKKS. So actually, even though these previous ones are older, more of the libraries now implement the CKKS because it's actually really good. It's a very, very good scheme. So this is the approximate computation. And TFHE is the only one that implements, TFHE. So they decided to name their library after the scheme. Well, advertisement. Yeah, well, actually, I would say that it's like a production quality homomorphic encryption library. Not many can say that, I think. And we've been working on this since 2015. We release patches often. We develop it really, really actively. It's our group's main project, probably at this time. It's MIT licensed, and you can just get it from GitHub. It should work on many platforms, almost all. We've been running it on some IoT devices too. This kind of thing is possible. Okay, there's a little lie there. I mean, it's possible to run it on IoT devices, but you need to like prune some stuff probably. Yeah, developed in C++ 17. Well, if you want to get started with this, there's a lot of examples there. Oh.
I've seen a Python wrapper for Seal called PySeal, but that's not developed by Microsoft. Would you say that?
Wait, sorry, what? What is it called?
PySeal.
Oh, PySeal. Oh, Python wrapper.
Yeah, Python wrapper.
Yeah.
Would you say that this is like safe to use or reliable, or would you recommend?
I don't think it's been developed in a long time. It uses a very old version of C, like 2.3 or
It's
something.
not the latest one.
It's very, very far from the latest one.
Okay.
Yeah. If someone wants to, I can say some words about the Python wrappers soon. One nice thing that we have for the C# wrappers, we basically have created a full C export library. So basically, you could just use that and build wrappers for any language. Anyway, to learn to use it, there's a lot of examples that are really, really commented in detail. So when I wrote these examples, I knew nothing about software engineering, or not really, and I didn't really know, because I wasn't really a developer, so I didn't really know how people learn to use libraries. These examples, these CPP files, they're kind of like, maybe you could think of it like a book. So you're supposed to sort of read it through all the comments. And if you don't do that, then you're not going to use it correctly. Like, it's absolutely necessary to read all of the comments and everything. So what we often see is that people copy paste, which is, so now I of course know that this is the normal way to do things. So you go there and you copy paste those examples, and it doesn't work, and then you change some things and suddenly it works. But this results in horrible things. So you shouldn't do that. That's not going to work in this case. Why doesn't it work? So this is really dumb. But for example, the very first examples, they explain things that you should never actually do. They show you how to do things in a very inefficient way. But I somehow thought that, well, it's like a good idea to start from these basics and sort of like explain this thing that's maybe easier to understand and then get to a little bit better stuff later. So it just doesn't go in an order that you would hope. But hopefully we're going to revise this in the future. It kind of starts with the stuff that you shouldn't use. Because it's easier to understand. It's easier to explain, maybe. Yeah, so actually, even if you read these, you're going to need to practice a lot. And I'm going to come back to this usability aspect soon. And you will, in fact, fail a lot. And you will fail a lot with runtime errors, unfortunately. And it can be very hard to get the top performance. But actually, the difference between a kind of a simple naive implementation versus a good implementation can be many orders of magnitude in performance. So this can be like 10,000x difference. And when you are thinking of implementing something and you do it, it can be difficult to know, like, where am I on that spectrum? Like, how could you know? That's a little bit of a challenge. So you better just just do it right. No, I'm just kidding. Actually, we're working on some solutions to that, and I'll tell you about that soon. So practicality. If you've heard anything about homomorphic encryption, I think it's pretty common that you would have heard that it's really slow and it's like unusable. This is because of something that I'm going to show you soon. But here's a little warning. So if you're a very sensitive person, and I'll tell you about this. But if you're a very sensitive person and you get easily offended or annoyed, just don't listen and don't look. So what happened is a lot of these people come ask me, okay, what's the performance overhead? And the real answer is, well, it's really complicated. Like, I can't answer that question. You have to look at all these different things. You have to kind of understand how it works. But you can't tell that to some vice president. So basically, I kind of just did this kind of curve. It's not completely imaginary. It's real. But obviously, I'll tell you why it's very hand wavy. But what you can see here, though, is the trend, which is that when it was invented in 2009, the performance overhead was something like 12 orders of magnitude, like 10 to the 12. It's like you can't do anything. They were thinking about maybe doing some XOR on encrypted bits. Since then, in fact, because of some US government projects and a lot of research in universities and a lot of investment also at Microsoft in our group, the performance overhead just kind of came steadily down until 2015 or so. At that point, it still continued going down until maybe 2018 because people were coming up with some more efficient algorithms for doing stuff. And in 2018-19, we started experimenting with GPUs and FPGAs. And actually, I'll show you something about that soon, but we can definitely get 2 orders of magnitude improvement from that one. Now, the real reason why this is hard to explain is that, well, here's some performance number table. I don't know how up to date this is, but that doesn't really matter. What matters here is, for example, first you need to say what encryption scheme you're using. So we're using CKKS. And then it says details. So this is the so-called fine print. So it says that multiplication times include relinearization, but not rescaling. In this CKKS scheme, for example, and in many homomorphic encryption schemes, you don't just do a multiplication. You might have to do some of these like housekeeping operations too. For example, this thing called relinearization or rescaling or something like this. And these operations, you may or may not want to do them. Some libraries kind of bundle them together with multiplication. Some libraries don't. And there's good reasons for both. And it's not necessarily easy always to say if you should kind of do it always after multiplication or not. So it really depends. Unfortunately, these things are more costly than the multiplication itself. So what do you say, I think? Should it include those or not? So I included the relinearization here, which is the costliest thing. Then here in the first column, we have this thing called polymodulus degree, which is one of the encryption parameters. This is basically the lattice dimension. So I chose 4 values here, ranging from 4096 to 32768. And bigger value here, bigger lattice dimension means more computational capability. And now you can see that when we report some encryption times, for example, there's a separate column for encryption and amortized encryption. Again, because we have that vectorization. So the difference is really massive. I mean, we're talking about some 1 microsecond there, and here we're talking about milliseconds. So the question is like, do you include that SIMD into your comparison? And finally, we can see similar differences in all these operations. Again, it's not really clear if the amortized times should be used or not. Okay, well, FPGA. So this is some very recent work that we did. We used the state-of-the-art FPGA, and we wanted to implement the CKKS scheme basically on this one. What that means in reality, it means that we take the costliest operations in the CKKS scheme, and we try to put it on the FPGA. And well, here's a really cute picture from the paper. It's some architecture diagram for one of these modules. But the very interesting thing here is, well, it's kind of hard to see here, but that number there is like 232, and that other number is 260 something, 268. And these are the speed-ups from FPGA. So these are really, really enormous improvements. And it's very cool, actually. This really takes the practicality to a different level. There is some fine print again, which is that we couldn't fit the biggest parameters onto the FPGA. So unfortunately, this doesn't go to like all the way to the slowest possible parameters. It would be fantastic if it would. Another challenge that we're encountering is that we've saturated the PCIe bus. So even with an ASIC, all we would gain is like bills. We wouldn't get any speed, because if we plug it in with through PCIe. Of course, luckily there's Ethernet, which is faster than PCIe, and it's possible to hook these FPGAs up with Ethernet. And it's possible to chain together many FPGAs with Ethernet too. So in fact, it might be possible to kind of go to the bigger parameters, but you would have to split your stuff across the different FPGAs. And it's possible. A lot of things are possible. We've also tried with the GPU. And we have some very good results from that, but it's like not nearly this fast. We're talking about maybe 50x improvement. But the GPU does scale better to big parameters. That's a fact. So regarding homomorphic encryption programming, I kind of already said something about this, that there's a big difference between like good and bad implementations, or good and kind of naive implementations. And here's what we can do. We can create a compiler, like everyone does these days. And we can create our own domain-specific language that better matches the programming model of encrypted computation. So if you're at all familiar with the secure computation community, you know that like this is the thing to do. Everyone has a compiler. So we need to create some automation. We need to create developer tools to help. We need to create some kind of debugger. We would want to have some IDE support maybe and whatnot. Actually, a lot of people have kind of worked on this already. We had a paper called Chet. It was specifically it was like a compiler for running neural network inference on encrypted data. And we needed the compiler because so a neural network is a layered computation basically, and the problem is that is with this vectorization again. It's when you want to do all kinds of matrix operations, vector operations through this neural network. These operations, they kind of can change how your data is laid out into the ciphertext slots. And the Chet compiler helped us figure out, okay, how do we best lay out our data, and how do we best do these linear algebra operations throughout the neural network, to kind of optimize the performance. Intel has been doing some work called ngraph HE, and ngraph HE2, which was just presented at CCS, or actually at a workshop before that. And another thing that we really need to create, and we want to create, is improved educational material. But this is a common problem for all modern cryptography, and not just that, it's actually a problem for all cryptography. If you're at all familiar with the usable security community, the state of crypto libraries is kind of, it's not the best. It's not so much about the libraries, it's also about the developer education. So universities don't really emphasize the security stuff. Here's a really silly slide that kind of shows what it looks like to write some very simple encrypted computation with the API from our library. So this is with the CKKS scheme. No. Well, the first box is obviously kind of a joke because it's very easy to compute 3 times 5 plus 7. But if you want to do encrypted 3 times encrypted 5 plus unencrypted 7, this is possible. What you need to do first, we call multiply in place, easy enough. But then you need to just know to do this relinearize. You need to just know to do this rescale. Actually, in some cases you might not want to do this, but usually maybe you would. Then you might want to do some scale renormalization thing, whatever that is. So you need to kind of read about that. And then you try to do an add plain. So you try to add your plaintext 7 to your encrypted product, and you're going to get a runtime error because you forgot to do the mod switch step. You ended up in some kind of parameter mismatch thing because of what this rescale does. So there's a lot of this kind of complex machinery and terminology that one has to learn to use it. That makes it kind of inherently not very scalable. to a lot of developers. This doesn't look too bad, but in practice the computations are much more complicated. And if you want to do some neural network evaluation, it can be nearly impossible to write it correctly. You're going to spend like the rest of your life debugging it. So it's trial and error work. You get a lot of runtime errors. Problems are usually not found at compile time, very hard to debug, no IDE support, all that good stuff. And of course, we're hoping to improve the situation with our compiler, and hopefully, we haven't submitted the paper yet. It's not public yet, but I'm really optimistic about the results, and it really seems like it's going to be easy to write programs, like good programs with this CKKS soon, because this tool will do all of this complex stuff automatically. It will figure out everything basically for you, and it will also optimize it hopefully well enough.
When are you going to publish?
When?
When are you going to publish?
I mean, we would actually release that compiler open source, so hopefully early next year. One thing that it does not do, though, is it comes kind of with this domain-specific language, and that language is still vectorized. So you still have to deal with those vectors, but at least you don't have to do all of that other really complex stuff. So we still, so it doesn't do like automated vectorization, but that can maybe be left at some higher level compiler. So, one of the first things that I did when I joined this group was this project called CryptoNets, where we were thinking, well, a lot of people want to do this neural network stuff, it seems, and it was really trendy, and we're thinking, well, what if we have a neural network? Is it possible to kind of take encrypted input and run it through that neural network and get an encrypted prediction of some sort? No one had done this sort of thing. It wasn't particularly difficult, it's just that no one had done it before. Of course, we used the simplest possible neural network in existence, or simplest possible dataset, kind of this MNIST dataset. But what we did get from that is that you write the digit, and you can actually run it through the neural network, and it classifies it even if the image is encrypted, and you get an encrypted prediction out, encrypted classification out. There's been a ton of work since then in this, like really all kinds of papers, good papers though, and all of these are about improving the speed, improving the performance, accuracy. All of these are purely homomorphic encryption, so they're totally non-interactive. What that means is that I take my input data, I store it in a cloud service, and the cloud service can at a later point predict on those. They get encrypted results which they can send back to me. They can update their neural network however they want. They don't need to deploy a new network to me or anything like that. Well, there's all kinds of hybrid approaches to make this easier. So this is not easy with homomorphic encryption. The reason is that we can only do those arithmetic circuits. We can only do additions and multiplications. And neural networks often use things like ReLUs and other non-polynomial functions, which we then have to somehow approximate, which is possible. Actually, it can work very well up to some depth. But there's also some hybrid approaches that use some multi-party computation to kind of deal with these kinds of non-polynomial functions. And typically in these hybrid approaches, the homomorphic encryption is used for encrypted linear algebra because it's very efficient. It's very good for matrix vector multiplication. Okay. I'm going to skip this stuff. Learning on encrypted data. Okay. Private set intersection is something really cool that is a relatively new project that we started in like 2017, 2018. We had some nice paper. And the idea is, of course, if you don't know what private set intersection is, the idea is that I have a set and you have a set, and we want to find the common items in our sets. And well, that's a little bit distracting. Let me take some beer. Okay. So we want to find the common items in our sets, but yeah, we don't want to reveal these sets to each other. So classical example, finding two companies want to find which customers they have in common. Another common example is this thing called private contact discovery, where you start using like WhatsApp, they usually say, and suddenly like all of your friends who are already WhatsApp users appear in your WhatsApp user list. And how does it work? Well, it's because it shares your list of contacts with WhatsApp, and WhatsApp figures out which of them are already using WhatsApp and tells your phone that they're there. So now you've just shared your all of your contacts with WhatsApp. But what we can do is instead we can do like a private set intersection of finding the common users. So this works, in fact, remarkably well. What we can do is we take so here's a database of some sort. I use the name as a key, and I encrypt my key, send it over to the other side, and the red here is privacy barrier. Nothing unencrypted crosses that. They simply compare that encrypted query with the dataset. They get an encrypted result, which they can send back to me, and I get, boom, found. Great. There's another variant of this which works really well, so let me just skip to the end. You can also retrieve some data privately. So in this case, we retrieve, for example, the email address. And in this entire process, the server or whoever hosts this dataset, they don't learn the query, and they don't learn what they return to you. And if the query doesn't appear in the dataset, then they just return non-random stuff to you. But they don't know that. And today we can actually reasonably kind of search through a set of at least 250 million items. So this technology, it stretches pretty well actually to quite large datasets. I would say doing something like a billion size, searching from like a billion size dataset is totally possible. And tables, so in fact many use cases don't involve such large tables. Usually when we would talk to customers about this, they would say, well, we have like 1 million items. And that sort of thing is very easy. We have, this is our second paper from 2018. And I'm not sure if we even did a 1 million size example there. Maybe we did, but that was like definitely the smallest experiments that we would have done. Some really sweet thing, if people know about these security models, this is actually like a malicious secure in some sense, which is remarkable because homomorphic encryption in general doesn't result in. It's very hard to build malicious secure protocols from homomorphic encryption, but this one is such. Other stuff that we can do, statistical functions. Why not? These kinds of things are really easy to do, even on large data, because these computations are all kind of low depth computations, low multiplicative depth. And
do you need a particular scheme to know the ways to an exponential?
I would use CKKS. For the CKKS scheme is the best choice for almost everything. One thing that we've actually done is, well, it's kind of related to the statistics, but machine learning also. We've worked on a Spark integration. So we've looked how to actually build Seal into Spark itself, and hopefully we're going to have some papers out soon about that. So I think I'm getting to almost the end. We have also a standardization effort going on, because why not? Everyone does that too these days. Because turns out that when you go to companies and you start talking about some new crypto, they're going to ask, oh, is this like US government standardized? And then what are you going to say? You're going to say that it's not. It's very well studied by a lot of experts. But to help with the situation, we decided that let's just create our own standardization effort, and hopefully in the future this is going to be merged with some kind of or picked up by some standards organization like IETF maybe, or IRTF, or IEEE, or well, there's a lot of possibilities. Even NIST maybe could be a possibility. So we've had a lot of participants from governments around the world, from companies, from academia, and there's a website, homomorphicencryption.org. And we've organized workshops pretty regularly where we discuss what's going on in the homomorphic encryption space, and we kind of try to develop these standards further. The most important thing that we have created is kind of a security standard. It's really important because before this effort, you would read all these homomorphic encryption papers, and the authors didn't really know how to even set the parameters necessarily securely. And when you have two papers that you're comparing, and one of them sets the parameters in a kind of really low security way versus another one which sets them in a much more secure way, then how do you compare? And if someone sets them incorrectly, is that a reject? So it's hard to... That situation was also kind of exacerbated by the poor quality of the libraries at that time. And it was a really serious problem. But now, of course, that's a little bit much better because we have a standard for the parameters and for how to estimate the security levels. So I think that's it.